Hello, and welcome to TutorTube, where the Learning Center's lead tutors help you understand challenging course concepts with easy-to-understand videos. My name is Calvin Garcia, lead tutor for computer science. In today's video, we will explore pointers. Sometimes, programs can get very large, especially when we declare a bunch of variables in our functions, our structs, or our classes. Pointers can help minimize the memory being used in our program, while also allowing for dynamic allocation of memory. In C and C++, variables come in a variety of value types. They all store a particular data type. Int stores integers, char stores characters, string stores strings, etc. That data is stored in a particular location in the memory. The location is marked by an address, much like your family's home is marked by an address. Whenever the variable is referenced by the program, the computer goes to that location in the memory to find our value. We as programmers can also reference our variables. You may have heard pass by reference. Just like our program gives the address to the computer to find a value, we can ask the program for the address of our variables. This is done with the ampersand symbol. This passes the address of the variable rather than the value of the variable. For example, if we declared an int variable of the name number, we could output the value using cout, number, and del. The console should then output the value and a new line. If we were to instead output the reference of our variable by putting the ampersand symbol before the name of our variable, using cout, ampersand number, and del, we would instead get the address of our variable. A variable's address is the location a variable's value is stored. What does that have to do with a pointer? Well, a pointer is a variable, but addresses are the value it holds. Wikipedia's hyperlinks that lead to other wiki articles are pointers to those articles. They use the address of the page to point to their location. A pointer is declared using the same data types as variables. To show a variable is a pointer, we add an asterisk. A particular pointer type can only store addresses of the same value type. This means, for example, int pointers can only store int addresses. Let's say we have an integer variable number. We can declare an int pointer called ptr by putting an asterisk before the name of our pointer. We can then assign the reference of our integer variable to the pointer by using the ampersand symbol before the variable's name. If we output our pointer, cout, ptr, and del, we will see the address to our variable. Which we can confirm by also outputting the reference to our variable using cout, ampersand, number, and del. What if we wanted to access the value inside the memory location? We would then use the asterisk symbol before our pointer's name, cout, asterisk, pointer, and del. This would instead output the value inside the address our pointer holds. Pointers don't need to be assigned variable addresses. We can also allocate the memory they use ourselves as programmers. Our program allocates the memory a pointer uses during runtime. If we have an integer pointer, ptr, we can allocate memory to the pointer using the C++ operator new. We can then assign value to the pointer by dereferencing using the asterisk. If we were to output the pointer, what would be displayed? What if we output the dereference pointer? Using the concept of dereferencing, we can perform arithmetic with our pointer. In this case, we will add 10 to our pointer's stored value. If we again output the pointer, what will we see? What if we dereference it? In both cases, we find that outputting the pointer displays the address. This address remains the same even after performing arithmetic to our pointer's value, which does change. What if we instead wanted to create an array? We would use the same new operator, but instead add square brackets. Inside of the brackets, we would need to declare the size of the array. There are many ways to dereference array pointers. One method is using the array notation, which uses the square brackets to denote the index of the array we are using. This makes sense since we allocated an array of memory. Another method is using the asterisk as before and adding the index to the initial address stored in our pointer. This is because the memory is allocated in series. Therefore, we can add to the address and find the next address of our array. To show this is the case, we can output ptr plus I and ampersand ptr I side by side. We know that referencing a variable gives its address. So the address ampersand ptr I should match ptr plus I, which is our initial address plus the index. When we allocate the memory ourselves within our program, the compiler and the computer don't know when to stop reserving the allocated memory slots, so we need to tell the computer. We do this by freeing the pointer within our program whenever we are done using it. In our previous example program, I did not use the C++ delete operator to free our pointer, but it still compiled. Again, the compiler does not know when we are allocating memory, because it is done during runtime. It is good practice to always free pointers to avoid memory leaks. In C++, this is done using the delete, as in delete ptr for single variables and delete square brackets, PTR, for array pointers. Though we did not talk about C allocation methods, it is important to note we cannot allocate pointers by combining C and C++ methods. That is, if we allocate using new, we cannot use realloc to resize the memory allocated. This is also true for delete and free. If a pointer is allocated using malloc, we cannot use delete. If a pointer is allocated using new, we cannot use free. Thank you for watching TutorTube. I hope you enjoyed this video. Please subscribe to our channel for more exciting videos. Check out the links in the description below for more important information about the Learning Center and follow us on our social media. See you next time.